So in this video, what we want to look at is what we call difference of two square. We want to look at how we will actually prove this expression that is called difference of two square. We have this a is raised to the second power minus b to the second power is equal to a plus b bracket bracket a minus b. And so look at this as a difference of two square. How do we actually factorize this? So it can actually be this, but what we are going to do is to prove that this expression is actually equal to that. And so we're going to take our time to understand the concept and how we actually go about factorizing, because whenever we see an expression with let's say you see a term is being raised, you have basically two term being raised to 2, and the thing is that anything that is substituted into these terms actually be squared, and the old concept of squaring and so on. But it is an expression that will always be equal to this whenever. And so what we'll do in this video, we will look at the proof, and then we go into another video with examples and practice questions. So let's go. But before we go, let us check our prior knowledge again. For the area of a square, area of a rectangle, factorizing or doing the distributive property, because this is what we're going to use to prove that what we are doing is actually accurate. But before we go to that, let us look at because it is very simple to factorize. Just a nice simple expression as this. I would actually find what is common in this expression. So the highest common factor will be 2 and 4. So we pull 2 out, divide 2 by each term. 2 into 2 goes x, and 2 into 4 goes 2 times. And so we actually have this in the distributive form. Well, the factorized form, we can actually reverse, because the reverse is when you factorize an expression, you can actually get back the problem by performing the reverse of it, which is a distributive property. And so we should ensure that we have that skill and knowledge to actually perform that. And so what we'll be doing now is to go into the proof and to see how it works. So let's go. So if we have a square looking at this, and if we were to label the dimensions of the square with the letter A, let's say A. And we know that all the sides are equal, but we don't have to write all the sides, all the dimensions of the sides. So we just only do 2 for now. So if we were to find the area of the square, we would actually multiply. The area of a square is the length, the side times its side. And so if we were to multiply A times A, we will get a squared for the entire area of the shape, because the area of the shape is a space that is inside of it, that is enclosed with these dimensions. And so this will be the area of the square. And so it would be A times A. Now if I were to draw another square, it's a smaller square, and so I'll actually draw something looking like this. Now if we were to label this square, we are going to use B to label this dimension, these dimensions of the square. So I could say B, 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 B. But we don't have to write all of that. We could actually just write a B here and a B here. If we were to find the area of this letter shape, we'd have to do the same thing as we did with the A's. So we'd say B times B, that gives us B squared. And so if we should actually examine this, if we were to find only the space for this part of this shape inside, we would call this an irregular shape after pulling out this part from it. If we were to find just the area of that, we would have to definitely subtract this new square, this new b square from the entire thing to get only that irregular part, which is all of these, all of this, all of that. Find the area. And so if we were to actually find the area of that, we'd have to subtract the b from everything, and so we have that little space there. But before we move on, let us try to understand something. Let us try to label our new dimension. Now this part would be b, this part would be b. Now if we were to find this part would actually be a minus this part, and so I could actually say a minus b. So if we were to find, because if just let us imagine if the dimension for this side, well, any side because it's a square, well, let's say this side it was 10. If I had 10, and so here would be also be 10 because these are parallel lines, and these are parallel dimensions, and they're actually equal. And so if this entire dimension, if it were 10, then if I should actually take away, well, share it with something, and I just want to find just this part only, I would have to subtract that. Let's say b is actually 3. I would have to subtract 3 from 10 to get only this part, because from here to here is 3, and from here to here is 7, just for argument's sake. And so we'd have to subtract that part from this part from whatever this part is to get that part only. And so this part would actually be a minus b. And so actually on our way. So what we want to do here, let me just write this, but what we want to do here is to take this square, I want to take this square right here. This square, let me take and draw it. I want to take this square right here. Take this square right here. This square, and add it to this part, which is extend this rectangle at the top. We actually extend this rectangle at the top. Extend it. So we actually extend it. But before we do that, let us also look at the dimensions, because the dimensions are very important. And so if we were to look at here, if we were to find here, this part, look at it very carefully. If this square and that square, so all of these squares have the same dimensions, and so this side would be b, that side would be b. If we were to find here only, just from this point to that point, then if this was originally a, we would have to do the same thing like we did here. So we will actually subtract b from here. So that part would actually be that part. And so this is very important to see before we move on, because we want to see some correlation with the new shape after adding pieces together. And so what we're going to do is to take this part, as we said, and put it right there. So after moving that, then we're going to try just to erase this part, so not to confuse us too much or any at all. So we're going to take this part and we're going to put it right here. So let's do that. So if I should take it, then I put it this part here, and I take this part right here. I hope it looks like a square. I think let's bring this over some more. All right. So look at this now. So everything here is removed. So we could even have this looking like that, because we already knew that it was going to look like that. And so if I should move this part now and put it right here, I would actually rotate it to ensure that this side is corresponding with this. Well, it's parallel to that, and so we'll actually write looking like this: a minus b. Well, we could have written it vertically. It doesn't matter. All right, so let's go. And so when I move this part, we have a minus b. And if you should look this part, well, this side, which was b, is going to be here. Because look at it, if we should take this part and we take it and we would actually rotate it, this part will be here, and while this part, which is b, will be right here. And so we can actually go and just erase this because we actually moved it. And so if you should look at this very carefully, we're actually seeing a rectangle at the top. We are seeing a rectangle at the top. So let me just finish. Let me just connect this. And so we're actually seeing a rectangle at the top. And so if we were to find the area of this rectangle, alright, so let us label this part. So this part should be B. So if we were to if we logically look at the length of this part, it will be actually all of this, which is A, plus that part, which is all of this dimension is A plus B. And if we should look at this logically, remember when we have a rectangle, we have two equal short parallel sides and two equal long parallel sides. So if this parallel side is equal to that parallel side, you can see it's looking at it. And so if this side is A plus B, then definitely all of here would be the same. And now, if we were to find the area of this rectangle, we have to multiply the length times the width. Let me use a different color. Multiply the length times the width. And so what's the length? The length is A plus B, and the width is A minus B. And so we prove that this is actually coming from that, or this is coming from that. It doesn't matter which way you look at it. So we prove it. And we could even do this, because this would be a factorized form coming from this. And so remember, whenever we do factorization, we can always perform the distributive property to bring it back to the problem. So we could actually multiply these brackets to see if we will actually get A squared minus B squared. And so we're going to do that to prove it. So this is the last part of it. Well, we actually prove it, but just to confirm that what we're doing is logical, it's very logical, and nothing say we're actually, just doing that part and just leaving it like that. No, let us see if it really makes sense. So we're going to say A times A gives us A squared. And we say A times negative B gives us negative BA, or AB, doesn't matter. And so we're going to do the same thing with the other side. So we say B times A give us plus AB, while B times negative B would give us negative B squared. If you should look at the middle term, these two will cancel. It's like saying negative 1 plus 1. And so they are opposite terms, and so they will actually cancel. And when they are cancelled, then we are left with just the two ends, which is A squared minus B squared. And so we have proven that this expression is actually equal to this.